Sting and the police might not want anyone to stand too close to them, so maybe they could use the APDS9960 sensor with a proximity function that will report increasingly larger values as objects come closer. I'm Prof G, and this is CircuitPython School, and in this lesson, we'll show you how to get this STEMMA-QT sensor working on a Raspberry Pi Pico or Pico W. We'll have a challenge and show a solution that'll light up a NeoPixel strip with more LEDs the closer an object comes to the sensor. We'll learn how to improve the code using Python slices. Big learning is rapidly approaching. Let's geek up! So friends, this board, the APDS9960, is a multi-sensing marvel, and the version that I'm using has STEMMA-QT ports, so wiring is as simple as plugging in a cable. Now this device can sense proximity, light, color, and can detect simple gestures like up, down, left, and right. And it can do this because the board has an infrared LED light. Now, infrared is light beyond the red in the Roy G. Biv color spectrum, so it's light that humans can't see, but our sensor can. And in fact, the light is detected by 4 photosensors in different locations on the sensor. So if you use this device, make sure that the sensor is facing forward with the lens facing out. Make sure that this front center part is not blocked. And another thing to note, this is called a proximity sensor, not a distance sensor. So it senses when things are close, but it doesn't tell precise measurement. For precise measurement, you'd want to look for a distance sensor, not a proximity sensor. There are lots of distance sensors that you can choose from. If you want to simplify wiring, you want to make sure you choose one that's STEMMA-QT. If you're interested in detecting more precise distances, check out other lessons on my channel. But this sensor might work well for very close proximity, something like detecting a hand is approached for dispensing hand sanitizer. And the sensor starts by identifying something from a few centimeters away, maybe about 4 inches or so, and at that distance you'll see an initial value move from 0 or 1 and start to change. But the numbers grow the closer you get to the device. So that's one thing that might seem a bit weird about proximity sensors. Distance sensors have numbers that get smaller as you approach because they report precise distance measurements. This sensor will show larger numbers as you approach, sort of like the way a Geiger counter speeds up as it approaches hazardous materials. Also be aware that these numbers don't go up evenly. So the gap between the numbers is going to be larger the further you are away from the device, and as you come closer and closer, those numbers are going to increase quickly. So the last few millimeters will run the numbers up. And here you can see in the output from the serial console, the plotter, and the number of lights that are lighting up. You can see small numbers, and when I get really tight, nearly touching the lens, we see the numbers really spike up. So let me show you how to implement this for simple readings, and then we'll have an LED strip challenge where we light up more LEDs as the proximity reading increases, like I just showed you. So working with this device in CircuitPython is super easy. First we import our library. I'll use this statement from Adafruit_APDS9960.APDS9960 import, and then in all caps, APDS9960. And also make sure that you've got the Adafruit_APDS9960 library inside of the lib or lib folder on your microcontroller. And even though we didn't import it using the import statement, your lib folder also needs the Adafruit_register library, but we installed that in our earlier setup lesson. If you don't have those in your lib folder, make sure you add them or your code won't work. Then we'll create the I2C object that we need whenever we work with STEMMA-QT, and then we can use the I2C object to create the sensor object. And we're going to name this object multi_sensor. We could use any name we want, but I like multi-sensor. I think that's a little easier to understand in your code than the letters and numbers that are the actual name for this device. It's almost like these devices were named by Elon Musk and Grimes. And then we create this object by using the APD9960 class, passing in the I2C object we created above. Then we turn on proximity reading by setting the device's enable_proximity property to true. And then we get a proximity reading between 0 and 255, with 255 being closer, by reading the dot proximity property from the multi-sensor object. And in this code, I'm putting this reading inside of a tuple, so the reading's surrounded by double parentheses, and I also put a comma at the end before the closing double parens. And in the prior CircuitPython School videos, we mentioned that this was how we could get these results to display in the plotter in Mu. And just a reminder from our earlier lessons on the STEMMA-QT standard, if you're wiring up a STEMMA-QT port to your Pico using this less than $1 cable, this is the wiring scheme I recommend. Blue to GP4, yellow to GP5, and power to 3.3 volt out. Any ground will do. Using this setup will let us create an I2C object using this code here, which is the same code you'd use on any CircuitPython board that had a built-in STEMMA-QT port. So let's code this up. So comment proximity sensing using the APDS9960. And I'm going to import board, comma, time, and from Adafruit underscore APDS9960.APDS9960, import, and in all caps, APDS9960. Then we'll create our I2C object with I2C equals board dot, and in all caps, stemma underscore I2C, open and close parens. This code works on the Pico and any board that has a built-in STEMMA-QT connector. Got a different board? Consult your Adafruit Learn Guide to see what code you need to enter here. Then we'll create our sensor object, calling that multi-underscore-sensor that I'm going to set equal to the class APDS9960, and we got to pass in between parens I2C, the I2C object that we created above. Then we need to enable the proximity sensor, so that's multi-sensor.enable_proximity, setting that equal to true. Then in our while true loop, make sure you add that colon, we'll print the sensor reading in a tuple so that it shows up in the console as well as in the moo plotter. So we say print, double open parens, multi-sensor.proximity, comma, close paren, and then we'll say time.sleep, and in parens we'll pause for 1/10 of a second, 0.1. Then I'll open my plotter and my serial monitor, and I'll save this as code.py to my CircuitPy volume, and let's see how we're detecting that proximity. So as I bring my finger close, we can see the numbers spike up. We see the plotter spiking up. Bring it away. The numbers get smaller and the spike goes down. So you can move your finger closer. Look right on top of it. That's where we get 255. Away. On top of it, away. You can move it back and forth and get a wavy sine wave kind of pattern. And now that you have this skill down, spectacular CircuitPython programmer, we're ready for a challenge. Now in this challenge, you'll code up the light strip behavior that we showed in the start of this lesson. We'll light up more LEDs as the proximity reading goes up, with all LEDs lit when the proximity reading hits its max value of 255. So we'll add a NeoPixel strip, and so that we can compare answers, let's call this strip. The signal pin will be connected via a variable named strip_pin. I'll use pin GP16 as my signal for the NeoPixel strip. You can use VBus as power for the strip as well. And I'll refer to the number of LEDs on the strip with the variable LEDs on strip. Now feel free to use any color. I'm going to use red, and if things are working properly, you should see results similar to the video at the right. Now you can do this using for loops, but as an extra challenge, if you watched the earlier lessons where we used slices, use slices to get your solution working here too. So give this a try, Code Monster. I know you can do it. I have faith in you. Why don't you pause, give it a shot, and when you're done, resume, and we'll compare answers. So before I change this code, I'm going to save this to my CircuitPython school folder on my computer with the name Proximity Sensing with APDS9960. Then I'll close this and open my code back up on my CircuitPy volume. I'll change the comment so it reads Proximity Sensing and LED strip using the APDS9960 and slices. And I need to import NeoPixel because I'm going to be using my NeoPixel strip. And let's set up this strip just before our while true loop with strip_pin equals board.gp16. That's the pin I'm using for my NeoPixel signal. And under that, I'll create a variable called strip_num_of_LEDs and set that equal to 30 since there are 30 LEDs on my strip. Then I'll create an object called strip, and I'll set that equal to NeoPixel.NeoPixel, capital N, capital P, and between parentheses I'll pass in strip_pin, comma, strip_num of LEDs. Then in while true, I'm going to delete these two lines here, and I'm going to create a value called reading, and I'll set that equal to multi_sensor.proximity to get my proximity reading between 0 and 255. And as a reminder, this is a multi-sensor. It can do lots of different things. So I'm going to put a comment up here to remind you, hey, make sure that you turn on proximity sensing when you're using this sensor as a proximity sensor. We'll learn some of this sensor's other capabilities in future lessons. Then below this, we're going to convert our 0 to 255 range, which is the reading that we get, to a 0 to 30 range, which is the number of lights that we want to light up. From 0 lights, no lights, to 30, all of the lights. The conversion is simple math that should be familiar to you if you've been going through the previous CircuitPython school lessons. We're going to hold the value of LEDs to light up in a variable called LEDs_to_light, and we're going to set this equal to reading times, and in parentheses we'll take strip_num_of_LEDs and divide that by 255, which is the max sensor reading. So sensor reading times max number of LEDs to light divided by max value for that sensor reading gives us the LEDs that we need to light up. In previous lessons, we might have done this on 2 lines, but this is pretty short math, so we can fit it all on 1 line. Now, one thing to remember, we can't have a fractional LED light, so we need to round this to the nearest integer. We'll put round out front and make sure that this whole equation is surrounded by parentheses. Then in our first condition, we'll say if LEDs to light double equals 0, colon, and indented below this, we'll say strip.fill, and we need to set up some colors. So below where I set up my strip, I'm going to set black equal to the tuple 0, 0, 0, and red equal to the tuple 255, 0, 0. Then I can say strip.fill in parens black, outdent, else, colon, but if I do light up some lights here, so my LEDs to light is greater than 0, then I'll use a slice to determine how many lights to light up. So I'm going to say strip, and in between square brackets, 0, my starting point to light things up, colon, LEDs to light, which is the end point for lighting up lights that I'm going to go up to, but I'm never going to reach. So I'm actually going to stop at LEDs to light -1, but you put LEDs to light in here because we never reach this value. And then we're going to set this equal to the color red, and since we want that repeated, LEDs to light times, we multiply this times LEDs to light. That's it. Now we got our lights lit up. We also want to make sure that we've turned off the lights that we don't want lit up. So I'm going to create a value for this on a separate line. The num of black lights, num underscore of underscore black underscore lights equals strip num of lights minus LEDs to light. Then I can create a strip slice below to indicate how many lights should be turned black, and that'll be strip, and in between square brackets, LEDs to light, colon, that's our starting point, strip num of LEDs. Remember, we'll go up to that value, but we'll never reach it, which is great. So this number is going to be 30 for us. We'll go up to light 29. We'll never get an index at a range value here. And we'll set this equal to black, and we want to repeat that, the num of black lights, so we multiply it by num of black lights. Now the correct number of LEDs should be lit up in red, and below this, just to make sure everything is working, I always like to print things out when I'm testing my code, so I'm going to say print, and in between parentheses, the F string, so lowercase f, between quotes, reading equals, set of curlies, pass in reading, comma, set of curlies, and before those curlies, I'll say LEDs to light equals, and in the curlies, LEDs to light. And I'll slow this down so that I don't overwhelm my serial monitor as the print tries to catch up with the board. I'm just going to say time sleep passing in 0.1, and let's save this and open up the serial console and see how things look. So let me adjust things and reach over and grab the sensor, and as I move my finger really close, we see the lights lighten up, and if I touch it, we see all the lights light up. Look at that. And the very last light is lighting up, so we don't have the issue we had in our previous lesson. So we can get all the lights up. We got to put our finger right on top of the sensor. So again, the sensor really doesn't kick in until you get very, very, very close, but we can see the slices and the light is lighting up exactly as we expected. We've got proximity sensing with the APDS9960. Yet another skill CircuitPythonista, nice work! So I'm going to double click on my tab and I'm going to save this to my computer in my CircuitPython school folder as proximity LEDs slices. Then I'll close this up and reopen code.py on my CircuitPython school volume so I'm ready for the next lesson. We sensed some big learning in the APDS9960. Hope you're feeling good about those skills. Continue to hack.